Yes, with a word of prayer. Thank you. Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask you just bless our efforts today. Help us to understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. So any questions about anything before I get started? Okay. So today I want to talk to you about the moment of inertia. For continuous masses. And so the basic idea here is we're going to think about some rigid body, all right, so some collection of particles that's stuck together, and it's going to rotate. All right, we're going to think about it rotating around its center of mass axis, right? And the key idea here is in that situation, the total kinetic energy, all right, is rotational. In particular, you can calculate it like this. You can integrate over the object, let's call it S, of 1/2 dm v squared. So last time I gave you the idea that we could just, calculate the sum of the kinetic energies for all the particles that are rotating around some, axis, right? Well, the continuous extension of that is to integrate 1/2 mv squared, right? And as long as all of these little masses are moving in the same way around the same axis, we could describe this another way. We can say, well, this is 1/2 times the integral of r squared dm times omega squared. Now here we have v is equal to r omega, all right? So this is the radius. This is the angular velocity. And by radius I mean the distance. It's the distance that dm is from the rotation axis, all right? So you're thinking about, you've got some axis of rotation. You're rotating it around omega. You've got this little dm out here. It's a distance r from the axis of rotation. All right? And so this thing I put in parentheses right here is what we call the moment of inertia. So, and you might say, well, what on earth kind of integral is that? So this is I, which is the moment of inertia. And so the answer is that integral is what it needs to be for the object that you're considering. Sometimes it's a one-dimensional integral, sometimes it's a two-dimensional integral, sometimes it's a three-dimensional integral. And we just have to slice and dice things according to the nature of the problem. So let's start out one-dimensional. Let's calculate the moment of inertia for a rod of mass m along length L. So here's example 1. So what we're thinking about, you got your rotation axis right here, right? And we've got some uniform rod here. All right, so its length is L. So you have mass, big M, uniformly distributed over 0 less than or equal to x less than or equal to L. So I'm saying L is the total length, and I'm going to use x. All right, I'm going to use x as the coordinate from the axis, right? So let me just draw a little picture here. So the idea is you slice this continuous mass up into little pieces, all right? So I look at a little chunk right here, let's say dm, all right? And this little bit of mass, it's going to be distance x from the rotation axis, all right? So the moment of inertia will always depend on your choice of rotation axis, all right? So it's critical in all of these calculations to understand where are we rotating around, all right? If you pick a different axis, you get a different moment of inertia. So it's very different than, it's analogous to mass, but on the other hand, it's very different. Since of course, if you ask me what your mass is, you don't ask me, well, with respect to what axis, right? It's intrinsic, right? But moment of inertia depends on the axis. So that's x. And so what's dm? Well, dm we can calculate as lambda times dx. Now lambda is the mass per unit length. Now what is that here? Since it's uniform, right? Lambda is what? It's dm mass per unit length, dm dx. But on the other hand, it's also equal to the whole mass divided by the whole length. So that gives me that this, in fact, is just m dx over L. All right? So to calculate the moment of inertia here, I have to do the integral over the rod of, r squared dm. But what does that mean in principle here? And here, this means the integral from 0 to L, right? My r for dm is what I'm calling x. So I have x squared. What's my dm? Apparently m dx over L. All right. And so we do that integral. What do we get? 1/3 m, my bad. 1/3 m over L, x cubed, right? Evaluated from 0 to L, what you got? I think these markers are extra squeaky today. So it looks like I've got a L cubed, right? The 0 thing doesn't contribute anything. So what I get 1/3 m L squared. So there you go. That's the moment of inertia for a rod of uniform mass density, which is rotating around its end. All right? So then we can ask other related questions, all right? So one of the first principles, so example 2, what if we instead of rotating around its end, what if we take the rod and we rotate it around its center, right? What if we make this our axis of rotation, right? Again, the same mass, the same length. What's the moment of inertia around the center? There's a couple different ways to do this. One way would be to do the integration again. We could set up the integral, right? We could integrate, take a little dm and calculate the integral, right? And we can go from like minus L over 2 to L over 2. You could do that. But there's another way to do this, which is to use a principle of superposition. So, and this is an important thing for examples. So let's use this idea. Instead of thinking of it as going back to base principles, let's think about it as just breaking it into two things, right? What is this? This is two rods being revolved around their end, right? But the one right here, the right one has mass m over 2, right? And the length of it is L over 2, right? And the same for the other side. So the moment of inertia here should be equal to the left piece plus the moment of inertia for the right piece, which we can calculate using the previous example. See, because it's supposed to be 1/3 the mass. What's the mass? Well, the mass for half of it's half the mass, right? And then what's the length? Half the length, right? Square that. And then I have to add that to itself again, right? So this times 2, right? Because these are equal, right? So just double it. So how does that work out? Well, this, I can think this 2 and that 2 cancels. I got a 3 here, I got a 4 here, so I got a 1/12. 1/12 m L squared. So there you go. This is the moment of inertia for a rod of uniform density being rotated around its center. And just like we saw last lecture, you get more, you get a larger moment of inertia when you have more of the mass further away from the axis of rotation, right? All things being equal. Yeah? Let's do a really simple example before I go on and do anything more complicated. What if oh man, did I not bring, oh there it is. So if you look at the notes, I actually do this example two ways. I do an integral from base principles, and I show it's equal to this, all right? So you can look at that. So this actually is example 3 in my posted PDF. So my example 2 is the straight integration. How about this? This is essentially a spherical shell, right? Is there any mass in the middle? I know you can't tell this, but it's blown up with air, all right? So the air is essentially massless compared to the mass of the ball, right? Let's just say that for the sake of for our discussion. So all of the mass is on this shell, right? What's the moment of inertia of a spherical shell as you rotate it around an axis through its center? So let's say spherical shell, mass m, radius r. You got the idea? So the r, you got mass m. We're supposed to do what? Integrate the integral. How's it go? By definition, over the ball, right? Although we call it a ball, but it's technically a spherical shell, right? R squared dm. How's that go? As you do the oh, wait a minute. Schnikes. It's not so simple. Oh, this actually is complicated. My bad. See, I was talking myself into everything is distance r away from the center. That's true, right? But you got to pick an axis, right? And as you rotate around the axis, how far is dm on the shell from the axis? It depends, right? It depends where you are. So if I take a little dm here, right? And I have my axis, let's draw it vertically. Well, the distance of this little mass right here is different than the little mass, like that's over here, right? So the moment of inertia is not going to be contributed to equally from different parts of the sphere. So how do you actually do this one? Yeah.
You take a hemispherical slice.
Take a hemispherical slice. Yeah, this was supposed to be a really easy example, but I talked myself into something wrong. So let's just leave this be. We'll come back to this one. This one so Sam's idea is right. We need to chop it up into pieces where we can easily calculate the little bit of inertia from each piece, right? So the right approach is something like you could think about it as a whole bunch of rings, right? You could think about it as a stack of rings, and since we can calculate the moment of inertia for each ring, we could add those up. I guess we could, but the details are fussy. See, because the rings are like this, right? Again, let me stop this for now. So we'll come back to this. Come back. I was just looking around my office for something I could actually bring and show you guys, and so I was so happy. I'm like, oh, I'll bring this, and then I didn't realize what I was getting myself into. So this integral is easily done towards the end of Calculus 3. When you learn about what's called the scalar surface integral, you can do this one. But so like the integral we have to do here in terms of Calc 3 notation is this, the integral over the ball of x squared plus y squared rho ds, where this is the so-called integral with respect to surface area. So you may not even be to that point yet in your Calculus 3 course, right? No, probably not. So, but your Calculus 3 course should get there. Let's see your example 4. See, that's why this Calculus 3 should be a prerequisite for this course, not a co-requisite, truth be told. Okay, example 4 here. Oh, where did I put it? Oh, there it is. Let's see here. It's actually not that bad once you have everything in front of you, but I'm hesitant to try to remember stuff off the top of my head from Calc 3 at the moment. Example 4, this one's easier. So suppose you've got a cylindrical shell. So this would be like a can without a lid, and you're just rotating it like this, all right? So cylindrical shell. Cylindrical shell, and let's suppose its radius is r, and it has mass m. So we want to calculate the moment of inertia. Now this one, the thing I wanted to do, I fooled myself into thinking I could on the last one, right? You can actually reasonably do here, right? We're integrating r squared dm over the shell, but the thing is, every single little bit of mass, right? What can we say about it? It's how far from the axis, right? You pick any little bit of mass on here, right? It's all distance r, right? Which means that when you do this integral, this is just equal to big R, and you can bring big R out, and you've just got integral dm. What's the integral of dm over the shell? If you add up all the mass, all the little bits of mass of the shell together, what do you get? You get the total mass, right? So this integral is just big M, and you just get m r squared. So this is the formula for the moment of inertia of a spherical shell. All right. So let's look at example 5. Example 5, what if we had a solid? So this one was a shell, right? What if your cylinder wasn't a shell? What if it's actually a solid? Solid cylinder. How do we do that? Then you have to think about slicing it up into things we can calculate the moment of inertia for, right? And example 4 kind of gives us a hint. Example 4 shows us that we can just write down the formula for a cylindrical shell, right? I can take the solid cylinder and I can cut it into a whole sort of family of shells, right? I can just like look at little shells like this. So if I do that, right? Let's say I go from, so let's say that this is x. Well, I don't know if I used x or r. Let me try to be consistent with my notes here. Oh yeah, I used x. So if this is x, then what's this thickness? What's the thickness there? It's dx, right? So if you just look at this shell, the the moment of inertia, the di for that one shell, would be, well, x squared times dm, right? But how do you figure out what dm is for a shell? So you guys have calculated volume by dividing things up into cylindrical shells in calculus, right? This was in calculus 1 for many of you. So I need to figure out what's the density here, right? Density, rho, we usually use in physics, rho for density. That's the mass per unit volume, all right? So here that's the total mass divided by the total volume. Well, what's the total volume here? Well, that's not quite defined until I tell you that we're looking at a cylinder here of length L, all right? So it's got length L, and I want to tell you it's got radius big R, all right? So what's the volume? Well, that's easy enough to figure out, right? Pi r squared times what? Pi r squared times L, right? That would be the volume of the cylinder. You don't need calculus for that, right? You should have known, known this in middle school, right? All right. So that's the density. So what I need then is what's the volume here of the shell? What I want is if I took that and laid it flat, I would have 2 pi x times L, right? And the thickness would be dx. So if you took this cylindrical shell and you just laid it flat, it would be the circumference of the circle, right, times the thickness, which would be dx, and its length L long. So that's what this is. So put it all together here, your little bit of inertia from the shell is what? It is 2 pi, I've got x times x, that gives me an x cubed, right? L m dx over pi r squared L. Let's clean that up. I think we can clean that up. The pi's cancel, right? And so what I've got is 2x cubed m dx over what? Over r squared, I believe. So that's just the bit of inertia from that one shell. Now to find the total inertia, what do? I add them all up, right? So I integrate. So integrating the total inertia here, the integral of di over the cylinder. What that means is you're going to integrate from 0 to r, because that's where x is going, from 0 to r, right? Of 2x cubed m dx divided by r squared. That's a pretty easy integral, right? Let's see, integrates x to the 4th divided by 2, so we got what, 1/2 m, and then we have an r to the 4th divided by r squared. So in total, we have 1/2 m r squared. That is the moment of inertia for a solid cylinder rolling about its axis. Oh, phew, that's what I got in the notes too. Well, you know. Now, if you understand the setup for this, right, you could easily adapt this to figure out what's the moment of inertia for like a thick shell, right? If you had example 6 is something like this. What if you have a shell where you've got some thickness like this? Now there's a couple different ways you could go with this one. It's probably worth talking about. Man, that seems wrong. Oh, that's right, that's right. Something funny happens with the algebra here. So B is the outer radius, A is the inner radius. So again, you have a mass m distributed about this shell. So it's hollow in the middle, but it's not a, we can't just use example 4 because it's not just all concentrated at one radius, right? So one way you could do this, right, is you could calculate the moment of inertia for like the whole kit and caboodle, like from all the way out to B. You could do it like this. But see, the reason that's tricky is if you were to think of it going all the way out to B and just like calculating the moment of inertia for the whole cylinder, then to be fair, you'd have to continue the cylinder to where it's empty, which would mean that the mass of that would not be m, it would be larger than m. So to like just straightforward rip off this calculation from example 5, it involves some kind of sneaky business. And so I think it's easier just to sort of just directly mimic the integration there. The thing which is slightly more complicated is that the volume of this is what? So the density, right, would be what? The total mass divided by the total volume. What's the total volume here? Again, I'm saying that this distance is L. So what's the volume? Well, it's going to be pi times b squared minus a squared times L. Right, so you take the volume of the outside cylinder minus the volume of the inside cylinder to get the volume of, this annular region. And so that's the mass per unit. This is your, dm dv. And once you know that, you can basically go back and just run through this again. And what you get is that I is equal to the integral from a to b of x squared times big M divided by pi times b squared minus a squared. The L's cancel. Well, fine, I'll put the L in. 2 pi xl. Again, the L's cancel, the pi's cancel. And what you get is 2m over b squared minus a squared times b to the 4th over 4 minus a to the 4th over 4. And the interesting thing is, this simplifies by algebra to 1/2 m times a squared plus b squared. So that is the moment of inertia of a thick shell of inner radius a and outer radius b. It's not at all obvious why that. I mean, there's like a line of algebra, but difference of 4th power you can factor, and then things cancel. Yep.
What was the reason again that you couldn't integrate the example 5 form from a to b?
So the tricky thing is we're saying that there's a mass m for just this shell. So to directly implement the previous example, I would have to do, what would be the total mass of the filled in thing? I would want to assume it has uniform density throughout, right? So I would have to take this density right here, right? So the mass of the filled in cylinder would have been, what would it have been? It would have been the density, which is this, right? Rho divided by pi b squared minus a squared L, right? Times the volume of the whole cylinder, which would have been pi b squared times L. So you could do that. You take this, right? This is the mass that we're talking about for like the whole cylinder with the same density that we're given. And you could take that mass and you could put it into the formula from example 5, and that would give you the moment of inertia for the solid cylinder of the same density as the shell that we were given. Then you'd have to subtract this same, then you'd have to figure out the mass for that you're deleting, the inertia that you're deleting, which would again be this density times pi a squared L. And then you take the difference of those things and you get to here. So, yeah. But anyway. All right. Let me stop writing and start projecting here at this point. This one that I'm about to show you, though, is more like your homework. All right, so while I'm waiting for this to come to life, let me go back to the one I punted on, talk about it for a second. So this one here, this ds, what that is the surface area element, and so that's actually r squared, and then you do goodness gracious. I want to say sine, well, let me just be a little bit, goodness gracious. I'm trying to remember, I think it's sine squared. So you guys are not to this point in the course yet. I think it's sine squared phi, or it's maybe sine squared theta. It depends on whether you're using math or physics coordinates, which is why my brain is not cooperating with me. But it's something like this. This right here is sometimes called d omega, because it's the solid angle. And if you integrate that over the sphere, you get 4 pi. Because you've got the polar angle and you've got the azimuthal angle, and they're asymmetric in their roles. But this thing integrates to 4 pi. And so, and then this x squared and y squared, you put in like, it's so this is r, and so if this is theta down here, this x squared plus y squared ends up, this is the other angle. I think x squared plus y squared is r squared, but r squared you can also write as rho squared sine squared phi. So when you, I think this is supposed to be a phi as well. When you put this all together, you end up like integrating sine cubed phi in order to get it. Yeah.
I don't think it's sine squared phi. I think it's just sine phi.
Is it just sine phi? You might be right. So I must be thinking, you know what? This is why I need to teach calculus 3 again, right? So thank you. But I'm thinking of the volume element, right? But so, oh, and like I was saying, when you multiply this times this, you get an integral of sine cubed. So I made a pair of errors. All right, let me close this thing out. I thought I had that example in my notes. You know what? I may be thinking of my Calc 3 notes. So anyway, my bad. All right. So long story short, I will look it up and tell you, or if I have time, I'll do the calculation next class for this. We don't have time today. But it's bigger. It's not mr squared, obviously, so it's smaller than mr squared because not all of the mass's distance r from the center of the rotation. I want to say it's like 2/5 or 3/5. I can't remember. It's bigger than this one. So here, this calculation I'm looking at right now, this is the moment of inertia for a sphere. And where'd it go? So I try not to. I've got too many things in this thing. That's not it. Oh, here it is. It's at the bottom. Duh. What? Oh, there we go. Sorry, I will come to my senses here in just a second. All right, so what I'm trying to say is the next example that I haven't written out yet is the calculation of the moment of inertia for a sphere. You have a homework problem that's based on this, all right? So your homework problem, it's like this, except that it's the old napkin holder problem. You've drilled a cylindrical hole through it. So you'll have to adapt this calculation to do that homework problem, all right? So here I'm trying to calculate the moment of inertia for a sphere of radius r rotated around a diameter. So what I do is I take the sphere and I chop it into cylindrical shells. All right, you guys know how to calculate cylindrical shells because you've calculated volumes with cylindrical shells, right? So we're just adapting that idea now for a moment of inertia. And so the dV, the little bit of volume for the cylindrical shell, is the 2 pi r, the circumference of the shell, times 2h, because that's the height of the shell, right? Times dr, because that's the thickness of the shell, where this is r is the distance from the axis, all right? And so the little bit of mass that you would get is simply simply dV times the density, which is we denote by rho here. It is unfortunate that we use rho for the spherical radius in like the Calc 3 course, whereas we use it for density in this course. It's just the way it is. So, sorry, worse than that, the physicists have this habit of switching the meaning of theta and phi for the angles, and engineers are typically with the physicists and against the mathematicians are on their lonesome in our use of theta and phi. But anyway, if you want to see like translations between these two worlds, it's in my Calc 3 notes. Anyway, so here we have the thing that makes this tricky here is R is variable, and let's see here what goes on. So the H, this is the part that's a little bit tricky is H is written in terms of R, and sadly I'm not, oh man, there we go. So this picture right here, see this is R, H is this distance. Big R is fixed, that's the radius of the sphere, right? So you can draw this picture on a vertical cross, like a slice of it, and you see the relation. H squared plus little r squared is equal to big R squared. So we can solve for little h as the square root of r squared minus r squared, like that. And so we just have to do that integral, which you guys can do. Here's the integral. It's just a u substitution actually, which is kind of nice, because we've got that like extra copy of r out here. So you don't actually have to do a trig substitution or anything too snazzy. Yep.
Can we go back up to the diagram that you have?
Yeah.
So is the second one, is that like a vertical slice out of the
Yeah, what I'm looking at is just the vertical slice of this. So if I were to superpose it here, it would be, I would think of it as like this, 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 and this. So this is not actually, you can think about this as the projection of this circle onto the vertical plane of the sphere or something like that. But, so for you guys, since you're drilling out, you've drilled a hole through it, right? So you won't be taking R all the way from 0 to big R, right? Your little r is going to range from some minimal radius, out to big R. And the minimal radius that it would start at, I think, would be the, the radius of the hole you're drilling, I suppose. But anyway, when you do the integral, which is not, you guys can do that, it works out to 2/5 mr squared. If memory serves me correctly, the spherical shell, it's either 3/5 or 4/5. I can't remember. But anyway. All right, so let's go on here. So everything I've been doing today is just to try to give you a sense of how we calculate the moment of inertia, right? But then we do things besides this, right? We like to, I don't know, you have something, right? And you don't just spin it in place. What do? We do what? We like spin it and throw it, right? You add a rotational motion and also a translational motion, right? So how does that work out? So that's what's next here in these notes. So let's talk through it. So basically, if you think about some rigid body, right? And the idea is it's moving through space, but it's also rotating around its axis through the center of mass. All right, so we want to describe a rotation around the center of mass axis. If I break down the position in terms of the displacement along the axis versus the displacement perpendicular to the axis, the displacement perpendicular to the axis is the part that has to do with the rotational motion. So in view of that displacement, you can calculate the formula for the speed, and you get it in terms of these three terms. There's the piece that depends on the velocity of the center of masses square. You've got another piece which depends on the relative velocity. We're talking about relative to the center of mass. And then there's this mixed piece. And so the little bit of kinetic energy associated with dm has three different pieces to it. It's got the part which is due to the motion of the center of mass of the system, right? We're talking about a rigid body. It's all stuck together, right? Like that ball I threw. And then you've got the part of the motion which is with respect to the relative velocity relative to the center of mass of the object, and then this thing over here. And so to find the total kinetic energy of the rigid body, you integrate. You add these all up, all right? And so there's three pieces. The one piece is you have 1/2 the velocity of the center of mass times dm. This gives you the kinetic energy of the center of mass, which is simply 1/2 m velocity of the center of mass squared. Very simple. That we usually call this the translational kinetic energy, all right? The other piece is rotational. And this is the piece we've been describing today in terms of you get this from 1/2 I omega squared, where I is the moment of inertia around the center of mass. Then this piece over here, the piece that involves the velocity center mass and the relative velocity, when you actually go through the details here, which are on the next page of the notes, this integrates to 0. So it turns out this piece doesn't contribute, and you can just find the total kinetic energy as a sum of two pieces for a rigid body. The translational kinetic energy of the center of mass and the rotational kinetic energy. So like, for example, if I want to describe to you the kinetic energy of this marker that I throw at you, right? There's two things. There's how fast it's rotating around its center of mass. How much kinetic energy, if this is rotating with angular velocity omega, how much kinetic energy, assuming this is a uniform marker? We calculated it. It was example 2, right? 1/12 ml squared. That's the moment of inertia. That times omega squared gives me the kinetic energy of the marker, right? And then how much translational kinetic energy? Well, that much. So if you could watch that, where does it, you know how marker will spin, or anything will spin? If you throw it, what axis it spins around? Ooh, what'd I hit? Is that the computer? I'm sure it's fine. So things will spin around their center of mass if you track their motion, all right? So it's not just an idle mathematical curiosity. That actually kind of describes how things will fly. I mean, will travel. So the rotational kinetic energy, again, going through the math here, it's just this. The relative velocity is given by r omega. And because of that, you can factor out the omega squared, just like I did in the finite case. And you get 1/2 this thing, which is nothing more than r squared dm. This is the integral of r squared dm. This is the moment of inertia we've been calculating today. 1/2 I omega squared is the rotational kinetic energy. Now, so here's the details of why that other term vanishes. It ends up being that the relative velocity is it's the coordinate from the origin. So like here's r prime, right? R prime is equal to the difference between your position relative to the origin and the position vector of the center of mass. So that's what we have here. And so when you integrate this, you have this minus this, but it turns out that as you integrate this over dm, well, that's exactly the definition of the center of mass. So you get the big R from this, and on the other hand, over here, since big R is constant, you just get integral of dm, which is m, and so they cancel, and this whole thing averages out to 0. So even though that term could be non-zero for a given mass, when you integrate it over the whole thing, it cancels out. Which is why it's important to us, because this gives us the thing we'll apply in all kinds of problems coming up soon, which is that the total mechanical energy has two pieces. It has the translational piece, which, so if I just do this, right? See this? I would never have made it as one of those, what are they? Baton twirlers? Yeah, people fall asleep watching me. But this right here, no translational kinetic energy, right? So all of the motion is purely rotational, right? Just rotational kinetic energy. If I take this, right, but then I do like this, then I gave it both rotational and translational kinetic energy. It had two pieces. To describe the motion, I have to understand both. Why hasn't there been rotational kinetic energy up till now? We didn't consider it. That's it, right? I mean, it's not that it doesn't matter. We've just been like putting a box on a plane and letting it slide. We haven't been like spinning it also, right? Now we're thinking about spinning things. And when we think about that, we have to take care of two pieces, the translational and the rotational. For example, if you have a cylinder of mass m and you let it roll down a plane and you ask what's the velocity of it, at the bottom of the plane, this is a pretty standard test question. How do you solve it? Well, you conserve energy, all right? So we're assuming rolling without slipping. And so if it's rolling without slipping, then kinetic energy is conserved. Excuse me, not kinetic energy. Energy is conserved. Total mechanical energy. But now total mechanical energy has two pieces. It has the rotational kinetic energy of the cylinder that's rotating, and also the translational kinetic energy of the cylinder. The translational piece we've already thought about before. That's still 1/2 mv squared, all right? But here's how it goes. You have the initial potential energy of the system, 1/2 mg r plus h, because that's where the center of mass is, right? So we think about the particle we think about the extended body as if it's a particle at its center of mass. And at the end of it, the center of mass is distance what? R above the plane, right? So at the end, I just have mgr. And so I have 1/2 mgr plus h, totally potential. At the end, I have my translational kinetic energy, but I also have my rotational kinetic energy. We worked out today that this I is what? 1/2 mr squared, right? 1/2 mr squared. So I put that in down here. 1/2 times 1/2 is a quarter. And notice that the mgrs cancel, so you just get mgh. It's 1/2 mv squared plus 1/2 m. See how this, why is there a v over r here? Rolling without slipping, the condition for that is that v is equal to r times omega. That says that the rotational and the translational are paired, right? As that wheel rolls along, it's tracking the edge of the wheel is just laying down along the ground according to the angle subtended. So anyway, we have, in short, I don't seem to have written it anywhere here, but v equals to omega r. So, or in other words, omega is v over r. And so what you get is 3/4 mv squared. So another way to look at this, it's as if, let's see, if you rewrote this as 1/2 times something, what would you have? If this is 3/4 is 1/2 of what? 1/2 of 3/2, right? So it's almost like when something's rolling, in this particular way, it's almost like it has 1.5 times the mass it would if it was just sliding. In some sense, it like gives you extra mass in some kind of sort of heuristic way. But anyway, and then you do the algebra, and there you go. That's the velocity that it has at the end of this. So anyway, how would this be different if instead of being a cylinder, it was like a sphere? What would change for this problem? What's that?
Side direction?
The what?
You go sideways?
No, we don't allow that. No. But yes, I mean in practice, of course. But imagine that we're stuck in this two-dimensional plane for the sake of not making things way more complicated. But things could be more complicated. You're not wrong. But then that wouldn't be part of this course, right? That would be a course where you had linear algebra, because that's what's needed. This is all very simplistic. Like to actually describe the motion of actual physical objects, you can't do it with just one number, all right? Like if your object is some funky looking thing like this, you know, and you want to describe the rotation of such an object, one number isn't going to do it. It's not a sphere or a cylinder, it's a sort of hexagonal turtle thing. They snap together and you can make bigger stacks of turtles off of them if you want. But you know, if I wanted to like look at the rotational motion of this, it's more complicated because it could be rotating different ways, right? If I rotated this way, it's different than if I rotated this way, you know? And so there's different modes of rotation. To describe these properly, you need something called the inertia tensor. And for that, you need linear algebra. But anyway, so this is just the first part of a larger story of classical mechanics. Anyway, we'll do more next time. Thanks, guys. Sorry I've gone over.